The Sudoku game is a common 9x9 Latin square type logic puzzle where all the numbers 1 through 9 must fill each row, column, and 3x3 subgrid without repeats. They have certain blanks pre-filled with set numbers or clues to ensure unique solutions. The puzzles can be modeled as a constraint satisfaction problem, or CSP. We chose to implement two different CSP methods for our Sudokus. The first was backtracking and uninformed depth-first search with limited forward vision. The second was the arc consistency number 3, or AC3 method, a popular backtracking enhancement technique that checks arcs between pairs of variables and has better failure detection than simple backtracking. Our goal for this project was to explore the Sudoku CSP by investigating the effects of differing algorithms and puzzle difficulties on Sudoku solution determination times. In addition, the solutions are widely applicable to other combinatorial problems.
In order to test various algorithms to solve a Sudoku puzzle, we implemented a program that would take an input of a 9x9 Sudoku board in the format of a 1D string with values from 0 to 9. The zeros represent empty cells, while the values from 1 through 9 represent filled cells. The program would then parse the string into a 9x9 board and run a specified algorithm on it. The output would then be the completed board and the time it took to complete. We tested the algorithms on a basic 9x9 Sudoku board of varying difficulty and compiled the times it took to run and averaged them to determine which algorithm could minimize the time it took to complete the puzzle.
We used 4 different puzzles of varying numbers of givens to test our two algorithms of backtracking and AC3. The first two puzzles had more givens to work with, so we predicted it would be less computationally expensive than the latter two puzzles, which had fewer givens. The third puzzle is actually claimed to be one of the hardest Sudoku puzzles for humans to solve, while the fourth puzzle features the least possible amount of givens. The first two puzzles both had 32 givens. We decided to test two puzzles with the same number of givens to ensure the difference in level of difficulty between the two would have no bearing on the runtime if we were given the same amount of givens. The result from these two puzzles showed that the runtime of backtracking was slightly better than AC3's runtime. At first, we were a bit confused why AC3 was running slower with these two puzzles, but then further results showed something interesting. When we ran the third puzzle, which had 21 givens, backtracking significantly started slowing down. However, AC3's runtime was practically the same. When we ran the fourth puzzle with 17 givens, the trend of backtracking slowing down showed again. In the end, while backtracking was faster for the puzzles with more given, it slowed down once we gave it puzzles with less givens. AC3, however, maintained a nearly constant growth, making AC3 the better saving choice for more complex puzzles.
During the process of working on this project, we faced many challenges. One of the key challenges we faced was trying to understand why our arc consistency 3 algorithm was running slower than our backtracking algorithm. We realized that this may have been due to the fact that the number of givens on the Sudoku puzzle were higher, and AC3 tends to do better than backtracking in puzzles that are harder and with less givens. As we tested puzzles with higher difficulty, AC3 ended up being more efficient. For future works, we would like to see different algorithms implemented, such as hill climbing and forward checking. We would also like to see what the runtime results are like on larger Sudoku boards. We think that this problem is important because not only is it helpful in solving real-world problems such as scheduling and steganography, but it could also be an important building block in future artificial intelligence research.